Alright you guys, this is video E3.2-4, notes for section 2.1, earthquakes occur along faults. Excuse me. The learning target is E3.2b, explain how scientists infer that the earth has interior layers with discernible properties using patterns of primary and secondary seismic wave arrivals. So, first off, we have to watch this video, complete these notes. You should have this set of notes out as we move through this. I'm going to close these and go ahead and open up the PowerPoint. Here we go. And again, please make sure you are using the pause button as needed. So rocks move along faults. A fault is just a fracture or a break in the lithosphere where the rocks are moving in relation to each other on the other side of that break. So a fault is just a fracture or break in Earth's lithosphere. Remember, our tectonic plates are lithosphere. It's all of the crust and some of that upper part of the mantle that has the same properties as the crust, where it's kind of hard and brittle. Number two, stress builds at faults as rocks stick and bend when trying to slip past each other. So if you can imagine holding two rocks up against each other and then trying to move them past each other, they're going to scrape past each other. And with that pressure, pressure can build up and build up if you're pushing them together a little bit before it slips. And that would represent an earthquake where those rocks finally give way and slip. But the definition here of stress is the force exerted when an object presses or pulls on or pushes against another object. If any of those things are happening, stress is building up. Earthquakes are the shaking of the ground caused by the sudden movement of large blocks of rock along a fault because of the release of stress. Earthquakes are because of the release of stress. Notice how this is italicized down here. Okay, whoops. All right, because of the release of stress. Shaking of the ground because of the release of stress is an earthquake. Strength of an earthquake depends on two things. One, the amount of stress that has built up before the rocks actually move, and then the distance that those rocks are going to move along the fault during the earthquake. Obviously, if a lot of stress is built up, meaning there hasn't been much seismic activity in that area for a while, no earthquakes, then a lot of stress can build up and we can have a big earthquake because a lot of stress has to be relieved. So in places of frequent earthquake activity, it's almost good sometimes to have, I guess, a lot of smaller earthquakes instead of having stress build up and have that big one. If a lot of stress is built up, there's a greater likelihood that the rocks are going to move a larger distance and we're going to have that big earthquake. For number 6, it says almost 80% of all earthquakes occur in the belt around the Pacific Ocean, also referred to as the Ring of Fire. So it's 80% of earthquakes and volcanoes on Earth are around the Pacific Ocean here, which is a plate in itself, the Pacific Plate, and it's known as the Ring of Fire. We are already somewhat familiar with this. Okay, so here's a map of some seismic data, and we can see the very active areas all around. See here where I'm pointing to is the Pacific Plate. Here's North America here in the North American Plate. But this is all one plate here. There's actually a plate here as well as in this area and here. And over on the other side here, this thinner line down here is our divergent boundary, the Mid-Atlantic Ridge, a mid-ocean ridge. But with all this activity, we have this great seismic activity here because of subduction zones. Oceanic crust subducting under continental crust. Those give us our biggest earthquakes and our most violent volcanoes. However, a small percentage of earthquake can occur within plates. The New Madrid Fault is right here in the United States in the middle of the North American Plate. And the stuff you're looking at here just says there's a probability of greater than 90% that, well, roughly a little more than medium-sized earthquake will occur within our lifetime. The problem with that happening here, and this is down in New Madrid is Missouri, basically northern Missouri, southern Illinois, where actually not too long ago there was an earthquake that some people around here said they felt a little bit, but that would certainly be felt here in West Michigan if there's a large earthquake. Several years ago there was, well, I shouldn't say several, 150, 200 years ago, there were 3 earthquakes over 8.0 on the Richter scale. As we're looking at this New Madrid Fault here, I said that was in roughly the southern Illinois area, and it's right in here. So New Madrid was right in this area here, but that strongest area felt was up through southern Illinois, and the problem with that is in this part of the country we don't build things. We don't need to build things earthquake resistant. Because of that, our buildings are not meant to withstand the shaking of the ground, and we would see a lot of building failure. And with building failure comes injury and death. We're in the 4 area for the modified Mercalli map, and what that is based on is observations. Okay, so it says in West Michigan here, this is about where we are. We would feel movement if we were indoors even. Hanging objects would be swinging like a chandelier, you know, a hanging picture or something like that. Cars would rock on their shocks. We'd see them moving. Fairly significant about how earthquakes affect people down the road. So faults. Faults are classified by how rocks are going to move. All right. Meaning in respect to the rocks on the other side of that crack or that fault. Are they moving? Is one moving up compared to the other? Is one moving down compared to the other? Are they sliding past each other horizontally? Could be lots of things. So there's 3 main types: a normal fault, a reverse fault, and a strike-slip fault. I will tell you the normal and the reverse faults are the tough ones to keep separate. Strike-slip is simple. So normal fault. Stress that pulls rocks apart. Okay, an example, the Great Rift Valley. This is a divergent boundary. So actually, after you write normal fault here in this little definition, stress that pulls rocks apart, it is this diagram, and notice the big black arrows on here pointing outwards, right next to normal fault, divergent boundary. And we see this footwall and the hanging wall and the hanging wall and footwall separating, the hanging wall dropping down compared to the footwall as they're moving apart. But I need you to have in there that a normal fault is associated with a divergent boundary. Right, divergent boundary right next to this. The opposite of that is reverse fault, and this is stress that is pushing rocks together. In other words, we're building mountains. The Himalayas are the largest mountains on Earth, where India is crashing into Asia still to this day. And when we look at those earthquake epicenter maps, we see that this place on Earth is riddled with seismic activity. So next to reverse fault, though, I need you to write convergent boundary. Reverse fault is a convergent boundary. You see these big black arrows pushing inwards in this diagram, and we see the hanging wall rising or coming higher than the footwall. But a reverse fault is associated with a convergent boundary. The last one is a strike-slip fault, and this is, I said, is the easy one, because this is stress that is pushing rocks horizontally past each other, okay, laterally. The example is a San Andreas fault right here in the United States in California. You guys have probably heard of San Andreas fault. This goes with a transform boundary, where the 2 plates or either side of the fault are sliding past each other horizontally. Okay? Hey, that's it.